Hello everyone, sequence, series, and proof. Day number 2. Topic for today is using what we know about sequences and series, both arithmetic and geometric, to do some word problems. So let's get started. Okay, example number 1. An architect designs a cinema that should hold 570 seats. The front row holds 30 seats, and each consecutive row after holds 6 more. So this tells me this will be an arithmetic sequence or series problem. Since I know that, looks like first row we would call a sub 1, that would be 30. Common difference would be 6, right? So the change from term to term, or row to row in this case, would be 6 seats. And it looks like the sum of the number of rows in the auditorium or cinema is going to be 570. I don't know how many rows there are, but looks like in part A I'm going to find that. So I'm going to use this formula. The sum of the first n rows or terms would be n over 2. 2 of the first term plus n minus 1 times the common difference. I'm going to plug those values in. That equals 570 times n over 2. 2a1 will be 60 plus n minus 1, well, I don't know n, times 6. Okay, so I'm going to solve that. If I multiply both sides by 2 and then clean up the inside, I'll get 1140. That 2 disappears. And then on the inside here, I'd get 60 minus 6 plus 6n, which would be 54 plus 6n. So it looks like I'm going to have a quadratic of some sort here. That will be 1140 equals 6n squared plus 54n. Okay, so I'm going to solve for n, and likely what I'll get in these scenarios, you'll probably get a positive value and a negative value. And of course, number of rows can only be positive, so we're going to work with that. Okay, so if I were to divide out a 6, this is very nice actually. A 6 divides out nicely. It becomes, whoops, where'd that 54 go? There we go. It becomes n squared plus 9n minus 190. Okay, so now I can factor. Factoring in this case, this is a relatively easy example. This would be n minus, would that be 10? And n plus 19. There we go, perfect. So that means n either equals 10 or n equals negative 19. Clearly, negative 19 is not a possible number of rows. So the cinema has 19 rows, or excuse me, 10 rows. Okay, let's look at the next part of this example. For optimal viewing pleasure, the floor of the cinema is tiered. Okay, so let's call this the screen. Okay, it says the steps between each row of the seats are 15 centimeters high. Each row is 95 centimeters deep, assuming that the front row is 3 meters from the screen and the ceiling is 2.4 meters above the last step. Determine the following. Okay, so the first row is going to be 300 centimeters, which is 3 meters from the screen. So then we go up. Let's do this in a different color. Let's go up 15 centimeters for every green segment we see. Okay, so then every row, like we said, is 95 centimeters. So we're going to continue to go up and over. For the entirety of the cinema, until we hit, I need green, there we go. We hit the very back of the cinema. Okay, and we're told that the back of the cinema, provided that the cinema's ceiling is parallel to the ground, it's not slanted at all, is what, 2.4 meters above the last step. Okay, so that would mean this would be 240 centimeters. Okay, so let's determine the horizontal distance from the screen to the back row of seats. Well, I know that I have 10 rows, right? So I have 10 of these red intervals, or rows of seats, right? And then I have how many of the green? So if I already have 2 rows, I'd have 1, 2, and 1, 2. So if I have 10 rows, okay, if I have 10 rows, then the horizontal width of the room would be 10 95s plus the initial 300. So in terms of n, if I wanted to do it this way, I would have 95n plus 300. So the width, or the horizontal length of the entire cinema would that be 950 plus 300. So the horizontal length of the cinema would be 1,250 centimeters. Now if it asks you for that in meters, just go ahead and move the decimal. You have 12.5 meters. Okay, let's look at the max height of the ceiling. Well, the max height of the ceiling would be the height of this wall, the screen there. So we would have the vertical, or the height of the room, based on n number of rows, would be 15 times n plus 240. So in this case, with 10 rows, the height, vertical height, the maximum height of the ceiling would be 15 times 10 plus 240, which would give us that max height in centimeters of 150 plus 240, which will end up being 150, 240, 390, which of course in meters would be 3.9 meters. Okay, let's try another example here involving maybe some finance. Okay, Jake turns 18. His grandparents contribute $10,000 into a savings account for him. The savings account collects 3% interest annually. Jake decides to contribute $1,000 each year on his birthday, starting on his 19th birthday until he turns 25. Okay, so let's talk first about what n will represent here. N equals 0 represents the year when Jake turns 18. So n equals 1 will be the year that Jake turns 19, all the way up to n equals 7 when Jake turns 25. Okay, so at the year n equals 7, Jake will be 25 years old. Okay, so that means, let's talk first about what would his account balance, right, be, and we'll call A of t, or A of n, the account balance in year n. Okay, so year n would be the number of years since he turned 18. Okay, so in year 1, in year 0, A of 0, Jake's grandparents contribute 10 grand. Great. So in year 1, when he contributes his first $1,000, he will have $10,000 plus, $10,000 times the 3% he earned on that, plus the $1,000 he contributes. Okay, and then in year 2, he'll have the $10,000 that he originally had times 3%, or in addition to 3%, plus the $1,000 that he had, and taking that total times an additional 1.03, which is adding 3%. So let me simplify that slightly here. That's the 10 grand he had originally, now being compounded at 3% twice, plus the $1,000 he had put in the year before, times 3%, and I forgot, plus the $1,000 he's supposed to add in. Okay, let's look what the third year would look like, and then we'll generalize this. It would be the 10 grand that his grandparents contributed, now compounded 3 times, plus the first 1,000 he put in when he turned 19, now compounded twice, plus the second 1,000 he contributed when he was 20, now compounded once, plus the 1,000 he contributed in his, what would that be, his 20 or 21st year, correct? So a to the n, or the nth year, right, would be 10,000 compounded n times, plus his first 1,000 compounded n minus 1 times, plus all the way down to the $1,000 he put in the nth year. Okay, which would be 1.03 to the n minus n. Okay, so we're tiering this off. So if we want to know how much he would have in his 7th year, that would be 10,000, 1.03 to the 7th, plus then a bunch of stuff, right? We would have the 1,000 times 1.03 that he first contributed to the 6th, that had 6 years of compounded interest on it. Then the 1,000 that he put in his 2nd year when he was 20, compounded 5 times. And we're going to have all the way down to the 1,000 that he contributed in his 7th year, or when he was 25. Let's assume that he contributes in his 7th year, right, which would be 7 minus 7, which would be 0. Okay, so this piece right here is what it is, right? Grandma and Grandpa contributed this, and it accumulated a certain amount of money. That amount ends up being, oh boy, where is it? There we go. Using my calculator, I get $12,298 and 74 cents. Thanks, Grandma and Grandpa. You earned me just over $2,000, almost $2,300. Now, the remaining portion is going to be a series that we can calculate. All right, so how would we determine how to write out that series? Well, that would be the series from n equals 0 up to 6. Okay, where this is my 0 term, then I got my 1st, 2nd, 3rd, 4th, 5th term, 6th term. Now you can pause the video right now and determine how you'd write the sequence on the inside, but I would go 1,000, 1.03 to the nth power. All right, so if I plugged in a 0 to start, I would get this term, plus, plug in a 1, you get the next term, plug in a 2, you get the next term. And if you use your calculator and you actually write this out as the first term times 1 minus r, which is 1.03 to the nth power, which in this case is not 6, it's actually 7, because there's 7 terms, okay, over 1 minus 1.03. That formula comes directly from the formula to find the sum of the first n terms of a geometric series, which is a1, 1 minus r to the nth over 1 minus r. Okay, this comes out to be 7,662.46 cents. Okay, so find the account balance the day after his 25th birthday. Well, I'm going to add these two values. And the account balance after, 7 years will equal, comes out to be, oh gosh, what is that, 19,961 and 19 cents. Not bad. Let's see in part B how much he actually made off of that based on what he contributed. So as we look, determine the amount of interest earned during this period of time. So interest will be equal to total, or amount, minus contributions. Contributions. Okay, so the amount that you have at the end minus the contributions gives you the interest that you'd made. So if I take my number, what was it, 19,961 and 46 cents, I believe. Nope, off. 19 cents. And I subtract contributions. Well, Grandma and Grandpa contributed a certain amount. And Jake, I think the kid's name was, from State Farm apparently, contributed $1,000 for 7 years. All right, so that's 19,961, blah, 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 minus 17,000. So it looks like over those 7 years, the interest that he had accrued was almost $3,000. Right? It was 29.61 and 19 cents. All right, awesome. It's a good problem. Hopefully you followed. You can see that geometric series take place there. And we'll see how it applies later on. All right, let's look at one more example. Carla traced back her family tree for 4 generations. Carla's parents are the first generation back, her first set of ancestors. Her grandparents are the second generation back and second set of ancestors. How many ancestors are in Carla's family tree? So here's Carla, her parents, mom, dad, her grandparents, grandma from mom, grandpa from mom, grandma from dad, grandpa from dad, and then she goes back from there, right? So as we go, here's generation 1, here's generation 2, we're going to go out to 3 and out to 4. Now I don't want to do the actual calculation there. However, what we do know is that each generation, the number of ancestors doubles. So the total number of ancestors in the generation n would be 2 to the n. Therefore, the total number of ancestors added up, or the sum, would be from I equals 1 to 4 of 2 to the n. All right, so this is a geometric series. You can see it'd be 2 plus 4 plus 6 plus 8, 2 plus 4 plus 8 plus 16. Okay, so we could see that if we added that together, we'd get 30. So she's got 30 ancestors, okay, in the first 4 generations of her family tree. Let's see how we would do that using the actual formula, not just pounding out the numbers, because clearly, if the number of generations gets large, it's going to be hard to add up all those numbers. Okay, so we would take the first term, if we were to add up the first n generations, 1 minus r to the nth power over 1 minus r. So in this case, the sum of the first 4 generations would be 2, 1 minus 2 to the 4th over 1 minus 2, which is negative 1. So that sum of the first 4 would be negative 2 times negative 15, right? 1 minus 16 is negative 15, and clearly then we get 30 the same way. Okay, let's determine how many generations back she would have to trace to find more than 1 million ancestors. Keyword here, more than, not equal to, more than. So let's find out when it's equal to. Okay, so we want to know, whoops, one more 0. I mean, it's basically like my paycheck. Okay, we want to know when the sum of the first n generations is greater than 1 million. So I'm going to take n over 2, whoops, my bad, a, which is 2, 1 minus r to the nth, which I don't know yet, over 1 minus r. Okay, 1 minus r is 1 minus 2, which ends up being negative 1. Okay, so I'm going to multiply both sides by negative 1, divide by 2. So it looks like I get negative 500,000, yep, is equal to 1 minus 2 to the nth. I subtract that 1, I get negative 500,001 is equal to negative 2 to the nth, so positive would equal a positive. So I want to know where 2 to the nth equals 500,001. So I'm going to take the natural log of both sides. You could use your calculator and just see on the graph where they're equal to, but I'm going to do it this way. This is more of a pure way to do this. Okay, now I'm going to bring that n down in front using the power rule of logarithms, and I'm going to divide by the natural log of 2. So the natural log of 500,001 divided by the natural log of 2 will give me n. And using my calculator, n comes out to be, it looks like 18.93 generations. Okay, so that's to equal a million, right? Equal a million. I want greater, so I got to go one number further, or in this case, just to the next whole number. So if you go out 19 generations, which is a long time, doesn't seem like it, but that is a long, long time, there would be greater than 1 million ancestors. All right, guys, that's it for day number 2 on word problems using geometric and arithmetic sequences and series. See you in the next video.